Well, welcome back to the lab. Today on the bench, we have a Tektronix 7704A. This is the 4-hole mainframe in the one of the 4-hole mainframes in the 7000 series. The 7704 is a 200 megahertz mainframe, so slightly faster than the 7603, but not as fast as the 79 or 71s, which are 500 megahertz and a gigahertz respectively. So kind of in the middle of the road, but a very common example of a 7000 series scope. There's a lot of 7704s and 7704As out there. From looking at them, the 7603 and the 7704 were probably the two most popular. So there's just a lot that are available. My serial number's pretty high, 242,000. So main difference between a 4-hole and a 3-hole unit. For the plugins, you get one more horizontal with the 4-hole unit. The other main difference between the two is the 3-hole units use a linear power supply. The 4-bay units use a switching power supply. So the power supplies between the two are slightly more complicated, but other than that, not too much of a big deal. So I've got to get this one calibrated and ready to go so I can get this over to the office. Figured I'd bring you guys along for the adventure. I don't expect there to be any faults with this unit. This one's one that I've had for a while and it's been sitting on the shelf, but I want to touch up the calibration before I put it back into production. So I've had the gear warming up for a while. I'll get started. Got the calibration document printed off, so we'll get started taking a look at this guy. Okay, so the power supply checks on this one start with the power supply out. So this is the top side of the power supply board. Here's one of the adjustments. The other one's on the bottom, right there. The other one's on the bottom. The unit is off at the moment. I'm about to power it back up. I did let it go through a warm-up time. You have to be extremely careful working with this power supply that's open. This generates quite a few power rails. Some of them are 200 volts plus. The other thing is all of this back here, all of the metal back here is ground. So incredibly easy to short something out. You don't want to do that. Okay, in my case, this is the 04 variant of this power board, so there is no 54.2 volt test point. So I start directly with the 50 volt, negative 50 volt adjustment, because that's the base supply for the whole board. So that's my adjustment for the negative 50 volts. So I'll get the meter hooked up and then we will check it. My tolerance on the negative 50 volts is plus minus 0.2, negative 49.99. So that one's good there, no adjustment needed. Okay, first things first is high voltage test point. So let me get the scope opened up and don't turn it back on because we need to hook up the high voltage probe. Okay, I've taken the cover off the high voltage power supply so you guys can see it. Test point 4221 is right here. Because you don't have any depth of field, you can't see very well. I'm nowhere near this connection. Comes down to the high voltage probe, which goes up to the Fluke 8840. Set on the appropriate range. We're looking for a reading of negative 2,960 volts, plus minus 29.6. We are actually very good. We're slightly on the high side. We're at negative 2,982. So that is within spec, but a little high. So everything is good with the high voltage supply. There is an adjustment on that though, 4123. I actually need to find out where that adjustment is, so I'll be right back. Here's the Z-axis board. It's actually on the other side of the scope. So our 4123 is going to be R23 on board 41. That's how the numbering's done on this particular scope. So it's a 4-digit number. The first set of 2 tells you what board. Second set of 2 tells you what component on that board. So this is board 41, so everything that starts with 41 is going to be on this board. We need resistor 23, which is all the way down here at the bottom, right here. So I need to adjust this for 2960, so I actually need to back this off just a bit. 2959.9. So we're allowed a tolerance of 30 volts, roughly 29.6, and we're within 300 millivolts on a 3000 volt supply. Good enough. Here's a close-up of the high voltage supply right before I put the cover back on, just so you guys can see what's in it. Main switching transformer is here. There's the rectifier diode there. Your test point is this wire loop right here. That's where your test point is. You can actually get that through the side cover. There's a hole to get a probe in there. I do not recommend doing this when this is open. This is low current, but it is 4,000 volts on this board. On the back side of the board, there's actually a voltage tripler. There is 21,000 volts on this red cable right here. So definitely not something, we're not talking about an inconsequential amount of voltage at the moment. This is 21 kV. And when you get into voltages up there, insulators start breaking down, things start getting jumpy. If you're following along, you're doing so at your own risk. So let me get the cover put back on, and we'll continue with the calibration. This is some dusty carbon buildup. I noticed it as I picked the cover up. I'm going to clean this off. This is just from the electrostatic, from the power supply collected on the bottom side of this plate. So we'll get that cleaned up before we put it back in. Okay, due to the fact that I'm working on the frame itself, I'm going to be using, there's going to be extensive use of the calibration module. So that's just, unfortunately, to work on one of these 7000 series, the plugins and stuff can be done, but the frame itself, you're going to need to have a module. I have 2 of the -1s, and I have 1 of the -2s. I don't have the older -00, so these are slightly faster than the -00, but they will work for any of the frames. I use the 01s to calibrate the 7603s and everything, so we are good there. We're on step 5, which is adjust the CRT bias. I'm going to need to set up a test oscilloscope, so I'll try to get both in the shot. If not, I'll show you what we're doing after that, and then we'll see what we get into. Okay, I have the test scope set up. 2 volts division, 0.2 volts division, 10x probe. I'm running a faster sweep just so you can see a line. They want 0.2 seconds per division, which would be 200 milliseconds per division, but the sweep is way slow, so it's really hard to do the adjustment there. So personally, I just sped the sweep speed up so I could see the line. We need to turn this on to DC. Okay, so we have a slow time base. Going to gauge the DC reference at 1 point. We'll call it 1.7 divisions of DC reference. Ground reference is where I expect it to be. And now it's down low again. So, okay, so there was, it got bumped. All right, so we're at 1 point, I guess 1 point. Yeah, we go right through 1.4. Okay, so we're good there. So now what we need to do is intensity control for 4 volts more positive than the level noted in G. So I need to bring that to 3. So I need to add 2 divisions of voltage because we're at 2 volts a division. So we need to go to, so we're at 1.4. So we actually need to be 3.4 up here. Yeah, 3.4. So what we'll do is we'll bring the intensity up. Okay, given the slow sweep speeds I was working with, I switched to a digital. I personally like digital scopes for very, very fast signals and very, very slow signals. Easier to use than the analog than their analog variants, just because of the persistence of the screen and the memory and everything like that. So we have a little bit of noise. That's what this popping is. That's just the environment. So I need to make the signal 4 volts more positive. So we have a max of 448. So we're going to go to 8.4. So we now have 8.4, and what we want to adjust is 4135 for a dot that is just extinguished. So move the camera back, and we'll make the adjustment. Okay, I'm going to make the adjustment now. I did not move that very far. Okay, so yeah, our sweep speed needed to be adjusted. Let me zoom in on this real quick. And for this one, I'm going to dim the lights just so I can preserve the life of the CRT. Okay, lights are dimmed down, but I can still see what's going on, so I don't short anything out. That is very important, especially when working with these, because there is many voltages everywhere. So what we do is we just bring this down till it just goes away. And to give you an idea, let me bring the lights back up because I can still see it just a bit. And just a touch. Bring it down just a bit more. There we go. Completely off. I can't see it, and the camera, which is more sensitive to it, can't see it either. Bring the illumination back up. White LEDs make the graphical look really nice. Okay. So that's grid bias. All right, I've gotten the measurement set up. So we're interested in this region of the pulse. So we want that to be an optimum square corner for the z-axis transient response, and you want to adjust R97 on board 41 and C109 on board 41. So let's see what R97 does to the response. All right, there we go. There's the variable capacitor. I'm going to get a non-inductive tuning tool. So as I add capacitance, we're seeing the peak kind of fall off there. So actually that looks pretty good, though slightly over adjusted. But that looks good for the corner. So that looks good right there for the Z-axis. So we'll drop that back down so we don't torture the tube. So that looks good. Disconnect all test equipment. All right, there we go. Let me find out what's next. Okay, I needed a full complement of plugins, so I'm going to let the other two warm up because this 26 and this 53 were not in there, so I'm going to give them their 20-minute warm-up time, and then we'll be back. Okay, this one was hard to set up, and we can see it's actually off, so I'll move this down and talk about the setup procedure for this one. This is step 7, adjusting the trace alignment. So what we have is we have a time base, calibration fixture, time base, vertical amplifier. Alt on the vertical, chop on the horizontal. Calibration fixture is frequency and step response. Both time bases are 0.1 milliseconds per division. When everything is all set up correctly, we get a nice graticule on, or we get a nice crosshair to align with the center. So there's 2 alignment points. This one rotates that way. That's trace rotation. Then we also have a vertical alignment as well. And we use the positioning controls to adjust it directly to center. And as we can see, we are off a bit on the rotation. Okay, this one's going to be really fiddly, so I will do it. You just got to do it a bunch of times, and when I get it all adjusted right, I'll bring you guys back. Okay, that's about as good as I'm going to get it, but that's pretty spot on. So we now have a X and Y are now lined up with the scope. Okay, we're going to adjust the autofocus. So at a very low intensity level, we make sure the trace is nice and focused. There's the focus. So then we turn it up to maximum. And then what we want to do is adjust the autofocus gain. Okay, so we get a good focus at low level. It's the smallest focus at high intensity. There's a lot of backscatter on that. That's why the beam kind of looks unfocused. All right, now we need a test scope, which we have. So let me set that up and I'll show you guys what that looks like. Okay, in this particular step, we can skip the bottom half because this 7704 has a different revision of the Z-axis board. So the H, I, J, and K don't actually exist. So I will get my other calibrator plug-in and I will show you the easy way to set geometry. Okay, using just the gain generator in the 2 calibration fixtures, we can generate a dot pattern that lets you do geometry. As you can see, it's off a little bit up top. So what we can do is we just adjust the geometry. for the best. I need to bring it out just a little bit. So my reference point is the two vertical lines, and then that's the reference. But then I'm adjusting based on these top dots and these bottom dots. That's what I'm adjusting against. And the geometry won't be perfect, but you can get it pretty good. Let me look at that straight on and see how that looks. Okay, that looks good right there. So there's the geometry of the tube. So it's a lot easier doing it with two calibration fixtures. However, two calibration fixtures I know isn't available to everybody. There is a geometry adjustment with a time-based generator and a few other things available in the service manual, and I have done it that way in the past. But if it's if you're going to work on a lot of these, this is much more preferable. Okay, I'm set up for part 9A. This is the shield volts. So the way I've got this set up is the vertical deflection plates are shorted out, which is these two pins in here. It'd be really easy if it was these two pins up here. It's not. It's down here. This is the vertical. This is the horizontal. I have ground set between the chassis frame and the vertical deflection plates just to see what they're at. And then I have to take a note on the meter reading. The meter is 36.287. So now I need to move the pin and then set the resistor for the same voltage. Doesn't matter what it is, just matters that you set it the same. Okay, P41U is shown on the center of the screen here. It's this connector right here, which goes into the tube over here, which you guys can't actually see. It comes up and goes in the tube. I need to measure pin 4, which happens to be the yellow wire on pin 4. So let me see if I can get a probe on that, and then we'll go from there. So I've got the probe on there, but it's really precarious. I can't really get in there with the camera running, but I have 36.280. I needed 36.287. Being off by 7 millivolts is not going to hurt it. That's good enough. So that one's done. Here's where I had the probes hooked up. This is the vertical pins. Be very careful with these pins. If you bend them, they go directly into the side of the tube. So that could be terminal to the tube if they get snapped off or something like that. So you want to be really careful with these pins right here, and you do not want to be messing around with a soldering iron in there. You could lose the vacuum in the tube, and that would be it for the scope. So, or at least the tube. You'd need to source a new one. Okay, for step 10, we're just checking the Z-axis input. All I've got is 50 kilohertz of 4 divisions of signal at 50 kilohertz going into a plug-in. Like we have down here, it's terminated in 50 ohms only because my function generator needs a 50 ohm input to get the levels right. So if I don't have 50 ohms, it doesn't output any power. So the 50 ohms is signal source dependent. This doesn't care about a calibration standard or anything like that. All we're doing is taking this cable, which is on the Z-axis input on the back of the scope, feeding that in, and the top half of the signal should disappear. So I'll unplug it, plug it back in. We do have disappearing of the signal, so that's done. The Z-axis input is working. That's all you have to do for step 10, which actually concludes the tube. So the next section is the vertical section of the scope. So I'll get everything set back up, and then I'll bring you guys back. Okay, 11, which is the vertical amplifier centering. It does say that it typically does not need to be adjusted, and I haven't replaced the CRT, or I haven't replaced any components or anything like that, and the acquisition unit is always been with this scope, so I'm going to skip that one. but it does want us to adjust the vertical amplifier bias. So I'll figure that out real quick, and then we'll go from there. Okay, so using the signal standardizer, we're on vertical or horizontal gain, 1 kilohertz rep rate. I'm adjusting 4415 for maximum deflection between the traces. So all I'm looking for is maximum deflection. So let me find 4415. That is in figure 632. So misadjusted. As I'm rotating it through its ranges, it's accordioning. So we want to hit it. That's a little too far. A little too far. Right there. There we go. Okay, I have everything set up for the vertical amplifier gain. Zoom in on the screen here real quick. Okay, as you can see, for this one we check between the 2nd and the 8th division, here and here. You line up the bright trace in the center and then check the deflection. It's 0.006 divisions, so we are a little off here. Not much, little. So what we'll do is we'll see if we can't true that up. It is R06 on board 44. All right, I need to be right on this for this calibration, so I'm going to move the camera out of the way, do it real quick, and then I'll bring it back. Okay, there we go. That's about as good as this one's going to get. It is slightly non-linear, so it's good down here. It's slightly off up here at the top. Not bad, within spec, so we're good to go. The next step is doing the same test, but doing it with the left bay as opposed to the right bay. And just to say nobody can say that I'm cheating. Calibration fixture in the left, plug in on the right, and we're set to left. And there we go. Did not need to readjust 4406, so this one was good. If yours is too far off, this is a compromise adjustment between the two bays. It's a compromise adjustment between the two bays, so you can get the best performance out of the scope. Okay, I'm going to zoom in on this here real quick. We're testing the low frequency linearity. So it's step response plus, rep rate 1 kilohertz, and 2 divisions of display. And what you're looking for is expansion and contraction along the display. This one is ruler flat. So this one is actually looking really, really good. I got a little bit of expansion, just a touch. Right here at the end, it kind of bows. You can barely see it, where this one's in the middle. This one's just the thickness of the trace below the line. Same thing on this side, so it's bowing just slightly. But the spec is 0.1 division. So that is under 0.1 division. It's the width of the trace. So that's about as best you could ask. So we'll dial this up to 1 megahertz. And a triggered display, but we want 100 nanoseconds per division on the time base. And what we are looking for is an optimum square corner on the rise. This is perfect. I am not going to mess with that. That is the high frequency compensation of the vertical channel, so that one is good there. I'll check the right channel here in a second, but this looks great, so I'm not going to touch it. Here is the high frequency compensation of the right hand channel. right-hand channel. And my reference point that I'm doing all the judging on is this square corner right here. This looks great as well. So I have good frequency response out of the vertical channels on this frame. Next up is we want to check the vertical amplifier bandwidth. So I will need to get a signal generator up and look for the 3 dB down point. Let me get that set up and I'll bring you guys right back. All right, well, I was working on the checking the vertical bandwidth, and it turns out the bandwidth was slow. So what that means, if you are working on one of these and you have plenty of, everything seems to be working and frequency response looks okay and everything like that, and your channel's slightly slow, it means this corner has been rounded off a little too much, and you've got too much attenuation or capacitance really in the signal, so your rise times is slow. So what I need to do is I need to adjust, I need to go through this table right here, and I need to adjust this corner is where I'm looking. Right here, this corner is where I'm looking to adjust it, but I need to sharpen that corner up and get some more bandwidth out of the vertical amplifier, because I'm supposed to hit 210 and I'm hitting negative 3 dB at about 180. I need to pick up 30 megahertz of bandwidth, so I'm going to get into that. The adjustments, just so you guys can see what I'm adjusting. Are these variable resistors and capacitors and this gimmicked capacitor right here. All of these variable resistors and capacitors around here, around the vertical amplifier, and this gimmick capacitor right here that you can barely see underneath these cables. So that's what I'll be adjusting. I'll bring you guys back after I get the adjustment done, show you what the corner looks like. The adjustment really is going through this table and playing with it and sharpening up the corner as much as you can without causing ringing or aberrations. So, be right back. Okay, after adjusting the high frequency compensation and doing the 3 dB down test, which is 8 divisions of display, wind the frequency up, taking note that the leveled light on the calibration fixture is on. That's leveling the frequency counter, or the frequency generator. We have 5.6 divisions of display. Everything looks good. And just to show we're not cheating, there's the calibration fixture, and I will move that up to here. And we're at 231 megahertz, so we are good to go there. Everything is working. So we make frequency spec barely, so I checked the other compartment as well. It's 230 megahertz on the left, 210 megahertz on the right, so these actually don't follow the same bandwidth spec. However, there's only one bandwidth adjustment on the board. So when you do it for the vertical amplifier, and then just make sure everything's in spec. It is. So we are good on the vertical channel. So I just need to check the vertical display modes and the vertical trace separation. So I'll set those up real quick, and we'll be right back. Okay, for this one it's just quick scope operation testing. So we have two vertical plug-ins. Both of them are grounded, but upper half, lower half, two traces, two traces. So this is chop, this is alt, add single trace, and to make sure add is working, yep. Yep. Okay. So that checks the, that's step 18, checking the vertical display modes. Set to right. And you need 2 horizontals for step 19. Point 2, point 2. Free running, auto AC int, yep. And we're doing the trace separation. That is working just fine. We can go off the screen. They just want above and below the center trace. So everything there is working, and that concludes the vertical section of the 7704. So we are on to the trigger system. So I'll get it all set back up there, and then we'll take a look at that. For the trigger section, I'm actually going to skip that. I read through it, and you just check the triggering section off of on a secondary oscilloscope. The triggering has been working absolutely flawlessly on this scope throughout the entire calibration so far. So if I was having problems, I would do this in depth, but there are no adjustments on here. It is just checks, so I am going to omit that for this run through. Okay, getting set up for the horizontal system. Time base, calibration fixture. Free running sweep at 0.1 milliseconds, and vertical horizontal gain with a rep rate of 1 kilohertz. Positioning the bright trace dead center. And we are off a bit here. Looks okay. So looks like could be a linearity problem, but we'll take a look at that here in a little bit. And we have our divisions from here to here, so that looks good. So I need to check the other bay real quick as the scope warms up. Yes, I do turn it off. All right, everything still looks good. So now we set this to triggering gain, and the vertical line should line up within 0.2. It does. It still does in the chop position. Everything looks good. But I can move it a little bit because I can do the horizontal centering, which is R25, which is right there. No movement when we switch it over to chop to check it, so everything is still good. And because I adjusted the centering, that will probably fix the deflection factor, so let's check that again. Second and 10th are still in really good shape, so that is good. That concludes step 22. Let me get set up for 23, which is the horizontal amplifier thermal balance, and I'll bring you guys right back. Okay, we can grab 10 nanoseconds. See if we can grab 5 nanoseconds, if this is even. Okay, we'll lock in at 5 nanoseconds. And it will lock in at 2 nanoseconds. So the high frequency calibration on the high frequency timing is working just fine. So I just have to check the phase shift now. Okay, here's the Lissajous pattern for the phase shift. And we're looking right here at the center for 0.28 divisions. We do beat 0.28 divisions. So we are good there. So I need to check the B compartment and just double check that real quick. and then we'll see what's next. And it looks like on the B side, we're good there. And there we go. So everything is all good. Thanks for stopping by the lab, taking a look at this 7704A. The frame needs a little bit of calibration. This is a scope that I'm going to put over in the office just for some random analog work that I end up doing. Doesn't do much with production or anything like that. This is just something for me to check out. These other plugins I've calibrated in other videos, so this is actually a fully calibrated unit, very similar to the 7603 over there. So just figured I'd do a 7704 because there was a couple of questions about it in the comments. So let me know how I'm doing, and let me know if there's anything else you guys would like to see, and we'll see what we can make happen. I will see you guys in the next video.